So we just learned all about the Tryptophan. And so now we're going to talk about the Lac Operon. So back up. Remember that the Operon is a bunch of related genes. So these guys all code for things that make tryptophan. So you need all 5 of them to make tryptophan. So they're all together. That's part of the operon, the regulatory genes. Then we have the operator and the promoter. Those are the parts of the operon. So this is the Tryptophan. When tryptophan is not present, it does not bind to the repressor. The repressor is inactive. It does not repress. It does not bind to the operator, so RNA polymerase can bind and transcribe all the genes that make tryptophan. So if there's no tryptophan, we make tryptophan. If there is tryptophan present, it binds to the repressor. It acts as a co-repressor with the repressor. Binds to the repressor. The repressor can then bind to the operator. See how it fits now? Then it blocks the promoter from allowing RNA polymerase to bind. No RNA is made. So if we have tryptophan, then we don't make any tryptophan. Okay, so a repressible operon is one that is usually on. The Tryptophan is a repressible operon. It's usually on, right? But when we bind the repressor to the operon, we turn it off. So a repressible operon is one that's on. It's able to be repressed. So the Tryptophan is a repressible operon. An inducible operon is one that's usually off, and so we can induce it. We can turn it on. So the one that we're going to talk about that's inducible is called the Lac Operon, meaning lactose. So we're still talking about E. coli here. And the Lac Operon contains genes that code for enzymes which break down lactose. So lactose is made up of 2 subunits. Is there a picture? No. Lactose is a bisaccharide, meaning it's 2 monosaccharides, which bound together are glucose and galactose. And so when the bacteria encounters lactose, meaning you drank some milk, now there's lactose in your stomach or in your intestines, it needs to break down lactose into glucose and galactose. And so what it does is it makes this enzyme called beta-galactosidase. And, let's say that anywhere. Anyways, beta-galactosidase is the enzyme that does that. And so the genes for beta-galactosidase, as well as other genes that have to do with lactose metabolism, are all in the same operon. So like in the Tryptophan, we had those 5 genes that made tryptophan. In the Lac Operon, we have genes that break down lactose. So by itself, the Lac repressor is on. Okay, so normally the Lac repressor is on. It doesn't have a co-repressor, nothing like that. It's active, so it can bind to the operator and prevent beta-galactosidase from being made. Okay, because there's no lactose present. So we don't need these genes that break down lactose because there isn't any lactose there. So the repressor is active when nothing's bound to it, so then it can fit into the operator because it is allosteric, meaning it can change shape of the active site. So when the repressor is bound to the operator, RNA polymerase cannot bind. We do not make the genes to break down lactose. Okay? So this is an inducible operon, meaning we can turn it on. We're going to turn on the operon so that we make these genes right here. And the way that we turn on the operon is the presence of lactose. Okay, so again, the thing that we're trying to make or the thing that we're trying to work with acts as the co-repressor, or the co-inducer in this case. So it's not actually lactose, it's something called allolactose, which comes along with lactose. But lactose, in the presence of lactose, the protein or the activator, the repressor, gets turned off. So with no lactose, the repressor is on. With lactose, the repressor is off because lactose binds to the repressor, changes its shape, cannot fit into the operon anymore. Okay, so we turned off the repressor. It's no longer repressing. So now RNA polymerase can bind to the promoter and it will make these genes. It will transcribe the genes for lactose. Now remember, it's making one mRNA molecule because there's only one promoter. RNA polymerase only binds once. It's making one mRNA molecule, which will be turned into 3 different polypeptides. One of them is beta-galactosidase, right here, which is the one that breaks lactose down into glucose and galactose. So, recap. No lactose, the repressor is active. It is bound to the operator and repressing the operon. The gene product is not being made. RNA polymerase cannot bind to the promoter. We are not transcribing these genes. They are not being turned into protein because there's no lactose present, so we don't need the genes. We don't need the protein to break down lactose. It's not there. If lactose is present, it goes and it binds to the repressor. It turns off the repressor. When it turns off the repressor, it turns on the operon. So we are inducing the transcription of these genes, of the operon. So lactose turns off the repressor, which turns on the operon. So the operon then makes the genes. RNA polymerase can bind to the promoter, transcribe the genes, then they get translated, and we get our gene product because we turned off the repressor. We induced the operon. So that's that. Do I have anything else to say about that? Okay, so the Lac Operon is an example of an inducible operon, and that usually has to do with catabolic pathways. Catabolic means we're breaking things down. Catabolism is breaking things down. So we have lactose and we want to break it down. It's a catabolic pathway. So catabolic pathways are usually inducible because as soon as whatever we want to break down shows up, like lactose, we want to break down lactose. As soon as lactose shows up, we turn on that pathway. That way we can break it down. On the other end, repressible pathways, such as the tryptophan pathway, are usually anabolic, which means we're building something. So in the tryptophan pathway, we are building tryptophan. And so it's repressible because as soon as we have built tryptophan, we don't need to do it anymore, so we turn it off. So repressible operons usually are involved in anabolic pathways. Inducible are usually involved in catabolic. But both of these pathways, even though one is inducible and one is repressible, both the Lac and the Tryp operon are involved with negative control. Okay, so there's positive and negative control. We're going to talk about positive in a minute, but negative control is when we turn off the gene in the form of a repressor. Okay, so it's negative because we are turning off a gene with the binding of our allosteric enzyme, the one that changes shape, in this case the repressor. The repressor, when it binds to the operator, it doesn't make transcription happen, it stops it. So it's negative. The repressor is negative, so it's negative control. Okay, but there is also positive gene regulation. And this is where it gets crazy because positive gene regulation is also with the Lac Operon. So the Lac Operon has negative and positive gene regulation. So what positive means is when whatever we're talking about, our allosteric enzyme, the one that changes shape, can be turned on and off, binds to wherever it's going to bind, it's going to turn on the pathway. Okay? This is different than our negative when it bound and it was a repressor and it turned off the pathway. So the operon, we're still looking at the Lac Operon, and now we're going to talk about something called catabolite activator protein, or CAP. This is an activator of transcription. So this is also about the Lac Operon, which is confusing, but this is going to activate the Lac Operon. Okay? So remember that the Lac repressor repressed it. It was negative control. Here's positive control. The binding of this molecule is going to activate it's going to activate transcription. So the reason for this is because bacteria, E. coli, if they have the option, they would prefer to transcribe, or they would prefer to break down glucose. It's easier for them than lactose. So they're only going to break down lactose if it's there and if glucose is not. If glucose is there, it's not going to break down lactose, it's going to break down glucose instead. So we have two things happening. Obviously, we're not going to break down lactose if it's not there. So That's obvious. But we're also not going to break down lactose if glucose is there. So we have 4 conditions. No glucose, no lactose. No glucose but lactose. No glucose, or glucose but no lactose, and both of them, glucose and lactose, okay? So when glucose isn't really present, we're low on glucose. Catabolite activator protein gets activated by something called cyclic AMP. So cyclic AMP is a co-activator, and it binds to CAP and turns on CAP, just like tryptophan bound to the TRP repressor and turned it on. Okay, so it's a coenzyme. So CAMP, cyclic AMP, binds to CAP, and then CAP is going to activate the transcription of these genes that we're talking about. So activated CAP binds to the promoter of the Lac Operon and increases the affinity of RNA polymerase for the Lac Operon. So it's the same spot that the Lac repressor was just binding, the same thing, the same genes that break down lactose, except now this CAP is going to bind and help bring the RNA polymerase to the promoter. That way it happens faster. Do I have a picture? Okay, so here's lactose present. So we want to turn on the operon, and it's inducible, we're going to turn it on, and glucose is not there. So the cell is going to say, okay, no glucose, but I have lactose, I'll break down lactose. Even though it prefers glucose, it will do lactose if no glucose is there. So lactose is present, so it is bound to the repressor. The repressor is inactive and it cannot bind to the operator. So the operon is on. But RNA polymerase might find its way to the promoter, but we want to help bring RNA polymerase to the promoter quickly. That way we can make these genes to break down lactose quickly. So that's the purpose of CAP. So CAP is activated by CAMP because when glucose levels are low, CAMP levels are high. So CAP gets activated by the CAMP, binds to it, now it's active. Then CAP binds to a special region in the promoter site called the CAP binding site, binds there, and then says, hey, RNA polymerase, come here, quickly, quickly. And RNA polymerase comes over and transcribes the genes to break down lactose. So they work together, the Lac repressor and CAP. If lactose is present and glucose is present, CAMP does not bind to CAP. It doesn't get activated, so it doesn't help the promoter call out to RNA polymerase. So lactose is present, so it's bound to the repressor, so the repressor is not binding to the operator, but nothing is really pulling RNA polymerase to the promoter region. So some of the Lac Operon will be made because some RNA polymerase will find its way to the promoter and it will make it, but it's not going to happen quickly like it does up here when the CAP is activated and is pulling RNA polymerase to the promoter region. Okay? Now, if there were, here's a big picture. If there were no lactose, so this is the lactose right here, the green. If there were no lactose, these Lac repressors would be on. They would be binding to the operator, and we wouldn't even be talking about this because the Lac Operon would be turned off. Okay? So this is only when lactose is present. When lactose is present, if there is low glucose, there's going to be a lot of transcription, but if there is high glucose, there's going to be very little transcription. So it's said that the Lac Operon is under dual control. It's under negative control by the Lac repressor. So the Lac repressor turns off the operon when it binds, so it's negative control. But it's also under positive control by cyclic AMP and CAP. Because if CAMP is there, because glucose isn't, binds to CAP, CAP binds to the promoter region and makes transcription happen. That's positive control. The Lac repressor provides negative control. So it's under regulation by both positive and negative control.